Okay, so good afternoon to everybody, and good morning to everybody for joining from across the globe. So today we are in the 81st session of Praktani Adda, and we have Sagnik Das as our speaker today. And to moderate the session, we have Sayan. He will be talking about molecular science, and without further ado, I would hand over the proceedings of the session to Sayan to moderate the session, and then Sagnik will start his talk. So, Sayan, now you can start.
Thank you, Satyanda. Thank you very much. So, welcome everyone to today's Adda. I am Sayan, and today it's my pleasure to introduce today's speaker, Sagnik Das. Sagnik Da completed his higher secondary in 2014 and then went to pursue his BSMS degree from Indian Institute of Science, Education and Research, also abbreviated as IISER, in Bhopal in physics. And after that, he started his PhD at University of Kassel in 2022, where he continues his journey deep into this academic world of atomic and molecular physics. And he's now in his final stage of his PhD, and which he is set to complete by next year. So before we
Brilliant.
dive into the physics part, let me just share a small personal story. So back in my higher secondary days in Vidyapit, I knew I wanted to do physics, but I don't have a clue what to do or what to do. So one day, few alumni visited in Vidyapit, and then one of them was the most fascinating, who has this long curly hair and have a look of a philosopher. And then we just asked him like what he does, and then he said that there is this college called IISER where you can do physics. And after that, we set the goal, okay, one of the target, let's say, and to go into the IISER. And as luck had it, we ended up in the same ISER, and for we spent a couple of years there, and then we also cross path every year in the annual DPG conference in Germany. And it was also thankful to Sagnikda that I joined this European chapter of alumni. I met Ritesta, Anupamda, and other people. So this moderation makes it a full circle. So just not to delay, now coming back to the topic, Sagnikda works in a like one of the very fastest regime that is possible, like going to 10 to the power minus 15 second, also called femtosecond. And in his recent work, he has shown that by using this femtosecond laser, you can control some chirality of the molecule, which is also important feature because it can turn medicine into a poison. So next time anybody wants to check a Glucon-D packet, you can know whom to call. So with that, I will let Sagnikda take over the stage, and over to you.
Okay, thank you, Sayan. Very, very flattering words by you. So I will share my presentation now. I hope you can see it.
Yes, we can see. You can
Okay.
make it full
You
screen.
can make it full screen, yeah.
Okay. Yes. So also welcome from my side. Welcome everyone. Good afternoon. Um, so um, 1 second. Yes. So firstly, I want to thank the organizers. Big thank you to Ritesh da, Satyam da, Sayon, who found time to uh, moderate this session. And thanks to everyone who has managed to join. Um, so today, I want to present mostly very general overview of this vast subject, and I have taken the liberty to modify the title of the presentation a little bit. And now it reads molecular movie and control with ultra short pulses. And let's start. So why we need ultra short laser pulses? To give a motivation. So if we want to make movies, then the general idea of photography comes to mind. And here in this left photo, what you can see is a bullet that has passed through an apple. So you can imagine this, the shutter speed of the camera that would take a picture like this should be very, very fast to capture such a fast motion. And these ideas also is relevant for the ultra fast timescales of molecules. On the right image, what you can see is a long exposure photo, and although it's aesthetically very pleasing, but here we lose a lot of information. For example, we don't know what these uh, light streaks are from, or what kind of dynamics is going on. For example, here in the sky, you can see some uh, light that is in circles, but we don't know what it is. Only after I read the caption of this image, I figured that this is a helicopter that is circling the sky at that time. So that's why to get the most information out of a system, you need something that is faster than the process to image that process. Okay. But why femtoseconds? So for us, we we mostly in everyday life measure time in hours, in minutes, in seconds even. And for fast processes, like when we, like in a race, or in a, yeah, like in a race, it's sometimes goes to maybe milliseconds. uh, in milliseconds there is also fast cameras. In milliseconds, milliseconds is also the time scale of uh, communication nowadays. So what I'm speaking now, or what I'm yeah, conveying now through the presentation, you receive in a few milliseconds. So uh, that's the time scale of milliseconds. And then faster time scales are of chemical reactions which can occur in microsecond range. And then comes the fast electronics. So your computer or your mobile phones, they it can operate in uh, range of nanoseconds. But then enters the world of molecules when we come down to picoseconds. So with picoseconds and femtoseconds, different molecular um, reactions or processes can take place. For example, in picosecond or femtosecond time scales, there can be rotations or vibrations of the molecule that that are present. And then, to my knowledge, the fastest physical process that can happen is electron going around the atom or molecule. Some of you may say that this is, of course, quantum mechanically, it's not a particle that is going around, but if we consider a classical picture, then the time scale of the electron going around the atom or molecule would be in attosecond time range. So that's why we need femtosecond pulses to look into these fast processes. Now, how do we convey what a femtosecond is? Because it's so fast, as already Sayan mentioned, 1 femtosecond is 10 to the power minus 15 seconds. And this is, I mean, it's really not possible to imagine, I would say, but still, to give a scale, we know the age of the universe, which is 12 or 13 billion years. And if we imagine 1 minute in that scale, then 10 femtosecond is 1 minute of that in the, if 1 minute is the age of the universe, or there are as many minutes in the age of the universe as there are femtoseconds in 1 minute. So 1 femtosecond is a very, very fast time scale. Okay, so now just three basic concepts, very fundamental processes in atomic molecular physics, which are the excitation, spontaneous emission, and stimulated emission. So it's very self-explanatory, but I will still try to explain. So if you have two levels and you excite two levels and the electron is at the lower level, and you radiate the system with an electromagnetic radiation of having the resonant wavelength, then the electron will be promoted to the higher excited state. Now, this electron does not live in that excited state forever. It can again come down to the lower energy state and emit a photon in the process, which we call as spontaneous emission. And this can happen randomly. There is no coherence in this process. However, if the electron is in the higher excited state and we come in with an electromagnetic radiation of the same energy difference, then this electron uh, uh, will come down to the lower excited state, and we will have now two photons of the same energy, and more importantly, coherent, that is, all the phases and everything are matched. So this stimulated emission is the basis of lasers. As all of you would know, laser stands for light amplification by stimulated emission of radiation. So this is how we can produce coherent pulses. Now, how do we make femtosecond pulses? So the most simply, what we can imagine is, I mean, this would never work in a lab, but just conceptually, what we need is a resonator, a cavity. So cavity is like two mirrors in which the light can keep on reflecting, and we need a gain medium to produce ultra-fast pulses. Gain medium like titanium sapphire is used. So sapphire is the main material, and then it is doped with titanium, and then you get some modified features which are more suitable for ultra-fast pulses. So you need such a gain medium, and we need to pump the gain medium, and then it would start to lace. But this cavity, one of the mirrors must be um, not fully reflecting, otherwise there won't be any pulse, any energy coming out of the cavity. So one of the mirrors is less reflecting, and hence we get some output. So in real systems, two-level system is not a good choice for lasers. However, four-level system is quite appropriate, which is also how the TISA works, titanium sapphire level system works. So, for example, the absorption and emission spectra of titanium sapphire are shown here. And if we pump the system with pulse with light around 500 nanometer, which is green in color, then it would then we can expect emission in the red, in the color red, around 800 nanometer, which is how most ultra-fast lasers work. So the basis of having the short pulses is that the spectrum in the frequency domain is broad. The spectral domain and the temporal domain are connected via the Fourier transform. So when we have a Dirac delta function in the frequency domain, that is a fixed frequency, then we will have a continuous wave laser. And likewise, when we have different shapes of the frequency, then the corresponding signal in the time domain changes. Most generally, we consider that we have Gaussian spectrum and Gaussian pulse shape. So here, this is a real spectrum of a laser, and then if we Fourier transform it, then we get the time domain picture of it. So I will just give some typical numbers of the laser system that we have in our lab. The average power is 5 watt, which is not huge. I mean, nowadays, not nowadays, I mean, for so long, there has been light bulbs that are more powerful than this. However, one must remember that this is not operating continuously. The energy comes in pulses, and for our laser system, the repetition rate is 3 kilohertz. That is, in 1 second, there are 3000 pulses, and each pulse is of 40-50 femtoseconds. And then the average power is 5 watt. So, which means within the pulse, there is huge power, and the average power is only indicative. Okay. So now I will give a general idea of what kind of light matter interactions can take place because now we have the light. So this is not a full list of different interactions, but most generally the light can be absorbed by the molecule, which is the matter, or the light is absorbed and the molecule is ionized. So in absorption, what happens? So this is basically fundamental spectroscopy. So we change the wavelength of our laser, and we see at which wavelength there is more absorption or less absorption. So more absorption would mean there is some resonant state at that wavelength, and less means there is no state. So for example, this is a typical absorption and circular dichrosine spectrum of the 3-methyl cyclopentane molecule. So this molecule will come back again in the presentation. So yeah, so you can see there are peaks, which means there are some states here, and then there are no peaks, which means there is no resonance. So after ionization, what we can look at are either the ions or the electrons. So if we look at the ions, then we can use a time of flight mass spectrometer, where we get the information about the different masses that are present. So in molecules, it's not just the parent mass, but also there can be fragmentation, for example, because molecules are bigger than atoms, right? So atoms cannot fragment, but molecules can fragment, and there will be signatures of that. In electrons, what we can see, so here, of course, one must make sure that the electrons is coming from only one molecule and not mixture of several molecules. But if it's coming from just one molecule, then we can have the information about the energy levels in the electron in the system. And for such studies, we need velocity map imaging spectrometer. And another aspect of this light matter interaction is the pump probe spectroscopy, which is, I would say, the aspect that makes that we can imagine as a molecular movie for us. So the concept is quite simple. We need to produce two identical pulses. So we have one pulse, and we create two identical copies of them. Or more generally, or it can be also two different pulses, but there has to be coherence between them. But let's say we have one pulse and we make two copies of them, and one of the pulses, which is the pump, it excites the system to one level, and then after a delay, we use the probe, let's say, to ionize the system. In this way, we can get the lifetime of the intermediate state. Here, for example, is the state S2. and we can also get the dynamics that's going on in the excited state. Just to give an example, so this is a ionization signal of a molecule, thiophenone, and here as we change the delay, you see there is a peak. So this peak is corresponding to the overlap of the two optical pulses, and thereafter you see some decay, and there is also some dynamics, or we think there is some dynamics going on in the system. And so I should have mentioned before, but Ahmed Zewail is credited for pioneering this kind of spectroscopy, for which he also got the Nobel Prize in chemistry. Okay, so once we know that there can be interactions of um, light and matter, we want to also control these interactions. So we don't only want to look at what happens when they interact, but also somehow influence their interaction. So for that, there can be at least two control parameters. Firstly, the intensity. So here the blue plot is, let's say, a high intensity, and the orange is for a lower intensity. And the intensity does play a huge role. It can completely change the interaction, how the light interacts with the molecule. And something more subtle is the phase. So if this is the envelope of the pulse, the electric field is denoted by this, the fast oscillations. And generally the absolute phase of these oscillations do not matter a lot, but in some systems, even this phase can control the interaction. And then there can be other kinds of phase control. For example, there can be up chirp or down chirp. So it's literally like chirping. So it's like the wavelength going from lower to higher within the pulse, or from higher to lower within the pulse, and that can have a different interaction with the molecules. So this is just so I will not go into detail in this slide, but here what I want to show, or what I want you to notice, is that in the plots from A to J, you can see that in the spectral domain, the spectrum is same for all of them, but the phase has been changed. So you start with no phase at all, and then you directly get a Fourier transform, and you know the time domain picture of that pulse. And similarly, you can change, like for example, this is a linear phase which shifts the pulse in the time domain, and then you have a quadratic phase that will broaden the pulse. Then you can have third order and such things. But what you can see, that the pulse in the time domain can be manipulated by playing with the frequency domain of the spectrum. And in these examples, even the spectrum is now cut from sides or cut from the middle, and many different manipulations are done, and the corresponding time domain pictures are shown. Now I come to the more direct topic to my PhD, which is chirality. So the chirality is basically when we have an object and we have a mirror image of that object, and they are not superimposable. A very nice example is our hands. The word chirality derives from the Greek for hands, which is I think care or care, something like that. So so our hands are chiral. which means that uh, they are not superimposable, and but they are the mirror images. And the chiral objects can interact differently with other chiral objects. So when I put forward my right hand and you put your right hand forward, then we can have a handshake. But if you put your left hand and I put my right hand, then it's not a handshake, it's more like holding a hand. Similarly, you can imagine like wearing shoes. The right shoe goes to your right foot and not to your left foot. So these are more, you can imagine like chiral interactions. Another chiral interaction more direct towards molecular physics. Let's say this carbon molecule, which is denoted here. It can have this R and S. So these are the two enantiomers of the carbon molecule. One of these molecules smell like spearmint, very fresh like mint. And the other enantiomer smells like caraway, which is shajira. So it's more like a spice. And our nose can detect the difference in the smell of these two enantiomers, which is, so it will not be always the case that our nose can differentiate the smells of two enantiomers, but for carbon, it's the case. Another infamous example is thalidomide. So in the last decade, in the last century, there was thalidomide was prescribed to women who were having the disease called morning sickness, and uh, there has been many negative reports about this medicine, and later it was found that one of the um, enantiomers is a medicine, whereas the other is a poison. So this caused a lot of defects at birth for people who use this medicine, but now it has been banned. Okay. Another interesting feature for chirality is the homochirality of life. For example, the sugars in that the naturally occurring sugars, for example, glucose or sucrose, are all right-handed, whereas the naturally occurring amino acids, uh, except glycine, because glycine is not chiral, the 19 other amino acids, they are all left-handed. So this is the homochirality of life, which is puzzling, but at the same time quite interesting. And we can't help but think what would happen it was uh, if the amino acids, for example, were not just left-handed but also right-handed. But at present, like this configuration is how uh, it is right now, and there have been many theories on um why there is more left or more right of these molecules in nature, but none that can concretely, yeah, concretely determine why it is the case. Okay, now coming towards yeah. So how do we detect chirality, or uh, yeah, how do we quantify chirality? So one method is circular dichroism. So to determine circular dichroism, we need circularly polarized light. As I already said, we need chiral objects to interact with chiral objects to know the chirality. So in absorption, in one of the enantiomers, for example, one uh, uh, one of the handed the left-handed light is absorbed more than the right-handed light, and in the other enantiomer, the opposite will be true. So that is how we can determine circular dichroism and hence quantify the chirality. And these are just formulas where you take the difference of the absorption, and then you can know if the absorption is chiral or not. So, and again, here I come back to 3-methyl cyclopentanone, which is the molecule of interest for us. And here you see there is a very small absorption band here, but we have a very strong circular dichroism in that band. And something that I am directly working in is circular dichroism in the ion yield. So extending from circular dichroism in absorption, which was just the first step. If we have more photons, we can ionize the system and then look at the differences in ion yields of the due to the two circular polarized lights, and then we can find the anisotropy factor given as this. So for that, we look into the ion yields. So this is basically the time of flight mass spectra of 3-methyl cyclopentanone. And in our setup, it is done in such a way that we get the ion yields from left and right circular polarized light within the same spectrum. So it's reduces a lot of statistical errors. So, and then you directly use the formula. On top, we use an achiral reference substance like potassium in this case. Here, potassium mass 39 is also present. So, potassium being achiral should not give any CD in ion yield, and whatever CD it shows is subtracted from the CD of the sample, and that's how we get the CD in ion yield of our sample. So this was recently also published, and we could show how different pulse parameters could control the CD in the ion yield of methyl cyclopentanone. I will just very briefly talk about what parameters influence the CD in ion yield. So we checked for pulse duration, we checked for the linear chirp, we checked for peak intensity. So we saw that with pulse duration, when we increase the pulse duration, the anisotropy also increases. And when we change the chirp of the pulse, the anisotropy also increases, but there is a preference to positive or negative chirp in some of the wavelengths that are used. And then for the peak intensity, when we change the peak intensity by reducing the intensity, then there is not a change in the anisotropy. But when we change the pulse duration and hence change the peak intensity, then there is increase in the anisotropy. So so we figured some parameters that can be used to control the CD in the ion. So what's next? So what is next with respect to, let's say, the 3-methyl cyclopentanone molecule is to do temperature-dependent studies. So in this molecule, two conformers are possible that is temperature-dependent. So the distribution of the conformers is temperature-dependent, and the more interesting fact in terms of CD is that they have opposite chirality, and hence their distribution determines the final chirality. So to do temperature dependent studies would be very interesting for us in the future. And the second direction from here is to look into the electrons. So we have already looked in the electrons in one of the cases, but to look at it in more detail, because as we see, there are many contributions from the states. So if we can resolve which state, how the CD changes from state to state, it could also be quite meaningful for us. So with that, I come to the end of my talk. This is just the acknowledgement slide. This is the Baumert group. This is Professor Baumert, who is the group leader. He's quite old. He's going to retire soon, but very enthusiastic guy. And this is Henrique, the project leader for me at least. I've been working under her project, and this is the complete chiral team here. So with that, I come to the end, and I look forward to your questions and the Adda session. Thank you for your attention.
So thank you very much, Sagnik, for the talk. And I ask the participant to ask what question they wants to do. So there was one question, not question, it was just a comment. কিচ্ছু বুঝতে পারিনি দাদা.
No, I think
Is Deep here?
I think people with science background would have found it worthy. People who have long left science, so someone like me who studied science last in 2013, so it was a bit difficult. So for sure,
Really? Okay.
Actually, that's the fact because you have gone so deep into it. So even a surface level thing might seem a
Okay.
very obvious thing to you, might not seem very obvious
Yeah.
to somebody who has long left science. But some things I did follow for um, so just one, because one area where we were talking about is importance in the pharmaceutical industry, whereas a particular molecular impact might have a
Yes.
different impact on people vis-a-vis another molecular thing.
Mhm.
So like are these kind of studies, so again it's more of a policy issue, that the kind of basic research that goes into the pharmaceutical industry that looks at the molecular level impact, so do these studies also are done by uh, pharmacy companies in Asian countries, or in particular Indian, or is the still research predominantly a western thing?
Mm, I I don't have an answer. I don't know if there are many Indian companies that are producing their own medicine, but I would imagine there should be some R&D department where they have to test these, yeah, the purity of the medicine or the purity of your sample. I mean, when we buy a sample, they give us the purity of it. So it's a bit involved, but it's possible to give the composition or the the composition of the drug that is being sold. So I think it should be done, but I don't know if in India it is followed as much or not.
Mhm.
I have a very generic question. Like I was just
Yes.
thinking like when you synthesize these chiral molecules, are
Yes.
there different synthesis technique for synthesizing a right-handed enantiomer or a left-handed one? Or is it more that you have to separate after synthesizing it?
Yeah. So yeah, I think it's both. So more generally, it is like you you produce the racemic mixture. So racemic mixture basically means you have equal amounts of left and right-handed molecules, and from there you use some chemical reactions to kill one of the enantiomers, and
Yes.
then you are left with more of the other one. But I would imagine there would be also reactions, or there would be also processes where you form only one of the enantiomers and not the others. And
I see. Hmm.
for chemists, CD is a very old thing. They don't really take it very seriously. They have uh, techniques that they can uh, use they use regularly to find the CD.
Mhm.
So, Sagnik, what's next after you submit your thesis? Do you want to be in academia, or You want to try something else?
I think I would like to try something else because it's a bit too much for me to stay in academia. It takes a lot. I probably not at this time. Yeah, I would probably try something else.
Just one more query. Like you have also studied in a prominent science institution in India, I said, and now you are in a university in Germany. So, what difference do you think there is in the research environment that you find maybe better or worse in Germany vis-a-vis you found in your parent institution in India?
So I think there are two aspects, of course. So in India, uh, also I was in a lab, in a molecular physics lab, and what I could see that it takes a lot of effort, lot of time to uh, get sample, for example, or get any new instrument in the lab, and the PI has to plan from 1 year ago to buy this stuff or that stuff. In in Germany, at least, it's the funding is not a issue. If you want something, you order it and you get delivery like within a week or something. Because also the big manufacturers like Thor Labs or other optics manufacturer are also present in Europe, right? So that yeah, you want something, you get it immediately there. However, in India, the somehow the your PhD guide is guide pushes you to do your work, or they will always try to get updates from you every week or every day. But in Germany, it's more for that what I found in the beginning, in the first year or two, that it's a very independent working system. And if you don't have the self motivation, then it gets difficult at sometimes. Yeah.
Yeah, I think in theory it is even more like if you are working in a theoretical physics, then in
Mm.
India there are opportunities of lot of discussion with other people,
Yeah.
but here it is more formal, I would say.
Yeah. I think that is also, I mean, because experimental physics, experimental science takes so much funding, so much infrastructure, that theory is more doable in India, I would think. And that's why there are so many theoreticians, prominent theoreticians in India.
I don't know if you know, but one of our alumni members is in Tata Institute of Fundamental Research in Mumbai. So uh,
Mm.
he also had because he's I think in India's best funded organization, supposedly the best funded organization, but he also had those apprehensions that again funding becomes a challenge at some point in time. Um, so I think that's a common issue that everybody at least I have spoken to has raised.
Yeah. So for me in academia, it's like never endingly you're always in a temporary kind of position. You never know what's going to happen in next 2, 3. Even after you get, for example, an associate professor position, still you have to search for funding every time. Your funding
Mhm,
ends in few years, right? And then again, next funding, next funding. So it's always hunting.
mhm. And just one more related question that again as you said that maybe academia is not something you are looking after your PhD. So for somebody who does pursue a career till what you have pursued, then what all opportunities in the private sector are there which can be.
So I have not looked very actively into the job market, but what I have heard from friends or colleagues is that, like in the optics industry, So there are big optics company that produces lasers or ultra-fast mirrors, or even small companies. There are quite a lot of openings in these kind of companies. Other than that, I could imagine uh, one with this time of flight techniques, or these, yeah, advanced detection techniques. Even pharmaceutical companies should be possible to, yeah,
Mhm.
they should also find some value in us.
No, no, sure, sure. Any more questions anybody else has?
Not a question, but just a suggestion, Sagnik. Maybe you can also talk to Anupam. Uh,
Yeah,
his lab is doing, I do not know what's the interaction between your field and his field. I'm not a science. Uh, but keep in contact with him because he
yeah,
also has a good network. If something uh, uh, attracts you, or you come along and he knows someone, it will be great to have you
yeah,
because we want to have scientific minds like you, we don't to flourish. So
yeah.
that's yeah. Thank you.
Thank you.
Okay, so I think as I could see, there are no more questions. So thank you, Sagnik, for this wonderful presentation. I am sure people who will watch it on YouTube or some other medium in future will benefit from it, and those who would be interested in the career path that you have taken so far would get in touch with you. And thank you, Sayan, for moderating the session. I think
No
both of
problem.
you took your time from your schedules, and that added value to our Praktani endeavor. So thank you all, and I think we can close the recording. And if somebody would want to have stay back for some informal discussion, then maybe we can stay back.
Yeah.